Greetings of the day to all of you. In our last lecture, we discussed about the advantages of shunt compensation. In today's lecture, we will discuss the advantages of series compensation. I will write here advantages of series compensation. Just like shunt compensation, series compensation offers the same advantages, like it increases the power transfer capability of an existing transmission network. It improves the voltage stability by providing voltage support. It improves the transient stability of the system, and it very quickly damps the power oscillations. Let us discuss these advantages one by one. So first is increased power transfer capability. Increased power transfer capability. We already know that I will write here, for an uncompensated system. For an uncompensated system, the power which transfers over the uncompensated transmission line, it is given by this equation: P is equal to V square by X sine delta, right? And now if the system is series compensated, it's compensated by, say, for example, a series capacitor, variable series capacitor. So I will write here, for a series compensated system. For a series compensated system, the equation for power transferred over the line gets modified because of the modification in the characteristics of transmission system. So the power transferred over the line is V square by X times 1 minus K into sine delta. So the denominator of this equation gets modified. X gets replaced by X into 1 minus K, where K is equal to Xc by X is called degree of series compensation. We already know it. So Xc is the capacitive reactance of the series capacitor, which is placed in series with the line. So if you draw the power angle characteristics for compensated as well as uncompensated transmission system, it will look like this. So for example, this is pi by 2, this is pi. This is for uncompensated system. The maximum power transferred, P max, is equal to V square by X. So this is for uncompensated system, where degree of series compensation is 0. Now if we go for series compensation, and the degree of series compensation may be 0.2, we may raise it to 0.4, 0.6, and so on. So depending upon the degree of series compensation, the power angle characteristic will change. It will be like this. For example, this is the power angle characteristic for series compensated transmission line with degree of series compensation as 20%, 0.2. And if we further increase the degree of series compensation, say for example we increase it to 0.4, so the power transfer capability of the line increases. So for any value of delta, you can see as the degree of series compensation increases, the power transferred over the line also increases, and the steady state limit or maximum power which the line is capable of transferring also increases. Okay, so this can be also verified if we write now, say for example, P1 is equal to V square by X sine delta. This is the this power transfer over the line for uncompensated line. I will, within brackets, just few moments back I had written this equation. I am reproducing it. This is for uncompensated transmission system. And P2 is equal to V square by X times 1 minus K into sine delta. This is for series compensated transmission system. Series compensated system. Now if we find the ratio of the two powers, for example P2 by P1, it is equal to V square by X into 1 minus K into X divided by V square, because sine delta is here, sine delta is here. When you divide the two, sine delta gets cancelled. This X cancels with this, V square cancels with this, so this comes out to be 1 by 1 minus K. This is very interesting relation. The ratio of power transferred with series compensation to the power transferred without compensation, that is P2 by P1, is equal to 1 by 1 minus K. Okay, now K is the degree of series compensation. So for example, for degree of series compensation equal to 50%. So for example, if you place a capacitor in series with the line with capacitor reactance adjusted in such a way that K is equal to XC by X, XC by X comes out to be 0.5. So degree of series compensation equal to 0.5. In that case, P2 by P1 is equal to 1 by 1 minus 0.5. That is 1 by 0.5. So that gives P2 by P1 equal to 2. Okay, so that is 1 by 0.5 is equal to 2. That means the power transferred by the series compensated line increases by 2 times the power transferred by uncompensated line. So therefore, if you if you have series compensation with degree of series compensation equal to 0.5, the power transferred over the same transmission line becomes 2 times the power transferred by uncompensated line. This is for degree of series compensation equal to 0.5. If you further increase the degree of series compensation, the line will be capable of transferring even more than this power. So therefore, this relation and these graphs clearly show that with series compensation, the power transferring capability of series compensated transmission line increases. And if you compare this increased power transfer capability of series compensated transmission line with shunt compensated transmission line, it will be very clear that there is higher and more effective series compensation than shunt compensation. Series compensation, I will write here this statement, series compensation is higher and more effective than shunt compensation, because you have just now seen that for degree of series compensation equal to 50%, the power transferred over the line becomes 2 times P1, okay, which is higher than the compensation provided by shunt compensation. Shunt compensation also increases the power transfer capability of transmission system, but series compensation series compensation is higher and more effective than shunt compensation. So that is about first advantage, that is increased power transfer capability. Second advantage is voltage stability. Voltage stability by way of providing voltage support. Voltage support. If we have a series compensated transmission system, radial system like this, for example, this is Jx, current is I, and I am compensating it by series compensator, capacitor, series capacitor whose capacitance is Jxc, okay, and it is a variable capacitance. I can adjust it, and we have a load. In case of shunt compensator with radial system, the shunt compensator was connected across the load. But in case of series compensator system, the series compensator, which may be a variable capacitor or a FACTS device, it is connected in series with the transmission line. So this is our sending end voltage Vs, and this is the receiving end voltage Vr or load voltage. Okay. Now we can very clearly see that when series compensation is done, the voltage drop across the line is Jix. Okay, or if you take the reactive, now this, as far as this current I is concerned, it has a resistive part or in phase component IR, which represents the real power consumed by the load, and it has a reactive or quadrature component of current Ix, which represents the reactive power drawn by the load. And as far as this reactive component of current is concerned, it is this reactive component of current which is responsible for voltage drop across the transmission line reactance, and it makes receiving end or load voltage less than sending end voltage. And if this reactive component of current is large, because reactive power is large, then this drop will be large and voltage regulation of the system will be very poor, which means receiving end voltage may be much lower than sending end voltage, meaning poor voltage regulation. In case of series compensation, when you are placing a capacitance XC of reactance XC in series with the line, there will be, in addition to reactive voltage drop JIX into X across the transmission line, there will be capacitive voltage across this series compensator. And what will be that? That will be JI into XC, or JIC into XC voltage, or JI into XC, where XC is the capacitive reactance. And this capacitive, if this is the reactive voltage drop, JIX into X, capacitive voltage drop is equal. You can make capacitive voltage drop equal and opposite to this reactive voltage drop. This will be JI into XC minus. Okay? Or if you don't make it equal and opposite to this this drop, reactive voltage drop, you can compensate for this voltage drop. That means if this is JI X into X, capacitive voltage drop can be JI into XC, this much. So that means the overall voltage drop across the line is nullified. This voltage drop is nullified, which means the voltage between the two buses increases. Without series compensation, this bus voltage minus this drop, and this drop may be very large. Okay, with series capacitive compensation, this voltage drop tries to nullify the voltage drop, reactive voltage drop across the transmission line reactance, and effectively it increases the voltage between the two buses across the line, so that you may be able to make it very, very nearly equal to Vs, and voltage regulation you will be able to improved voltage regulation. Okay, so this is how this voltage support is provided by the series compensation. Okay, now this series capacitive compensation, when it nullifies the reactive voltage drop across the transmission line, it produces a stiff voltage source across the load. So load voltage acts as a stiff voltage source. Stiff voltage source. Stiff voltage source means a voltage source which produces a voltage which is independent of the load current. Your load may draw larger and larger current. The load current or the transmission line current may vary, but this receiving end voltage will remain nearly constant because of support provided by this capacitive voltage drop. Okay, so this way you will be able to, or we will be able to improve the provide the voltage support, and hence improve the voltage stability of transmission system. So that will be very much clear if you draw the graphs. This is power drawn by the load in per unit versus receiving end voltage or load voltage in per unit. Okay, so for example, this is 1 per unit, this is 2 per unit, this is 3 per unit, this is 4 per unit. Receiving end voltage is 0.5 per unit, 1 per unit, 1.5 per unit, and so on. So it is something like this. This is, for example, the voltage, receiving end voltage versus power characteristic or graph for XC for XC equal to 0. Excuse me. This is for XC equal to 0. I should redraw it. This is for xc equal to 0. That means when there is no capacitive compensation, series compensation. Okay. Now when series compensation is provided, the graph becomes like this. This is for xc equal to 0.5 x. That means k, which is equal to xc by x, is 0.5. When 50% degree of series compensation is 0.5. And if we further increase the degree of series compensation, then our graph may become like this. This is for xc equal to 0.75 x. That means k equal to 0.75. So higher the degree of series compensation, the nose point, which represents the voltage instability, you can see it is substantially or appreciably it is shifted towards the right. So higher the degree of series compensation by providing the series capacitive reactance in series with the transmission line, the farther and farther this nose point will move towards the right, and hence it will improve the voltage stability of the transmission system. Okay, and you can see the drop in the voltage for uncompensated line is substantial. I mean, there is a steep drop in the voltage when we increase the when we put when the load draws more power. When load starts drawing power, there is steep drop in the voltage, so that voltage regulation is poor because of large reactive voltage drop across the transmission line reactance. But when we are providing the series capacitive compensation, with, for example, the degree of compensation equal to 50%, 0.5, the drop in the voltage is not steep. As you increase the power, no doubt there is a drop in the voltage, but it is not a steep drop. And you can see the voltage, this nose point is appreciably shifted towards the right. And when you further increase the degree of series compensation from 50% to 75%, 0.75, the voltage almost remains constant. There is a very small drop in the voltage from no load to say 3 times the full load, 3 times when power is 3 per unit. And you can see the nose point is further shifted towards the right. So therefore, by providing series compensation, the voltage regulation of the transmission system is improved, number one, and number two, the voltage stability is also improved by shifting the nose point or voltage instability points towards the right. Okay, so this is about second advantage, that is voltage stability by way of providing voltage support. So series compensation substantially improves the voltage stability of transmission system. Third advantage is transient stability improvement. I will write here transient stability improvement. Series capacitive compensation improves the transient stability of the transmission system. This can be explained with the help of power angle characteristics for uncompensated system and for series compensated system. Let me draw these characteristics and then I will explain. This is pi and this is P max equal to V square by X. This is, for example, figure A, uncompensated system. Uncompensated system. Let us assume the system operates, this PM is equal to PE. The system initially operates at a power angle or transmission angle of delta 1. Then fault occurs. Let me first of all, draw the diagram, and then subsequently I will explain. Please bear with me. Let me first of all complete this diagram. This is delta 2, this is area A1, and this is delta 3, this is area A2, which is equal to area A1, and this is the margin of stability, A margin. This angle is called critical angle, delta critical. Okay, this is for uncompensated transmission line. For series compensated transmission line, delta, the power angle characteristic will be like this. So I am now drawing figure B for series compensated system. Series compensated system. Okay, fine. So this is pi. Okay, now this is mechanical input equal to electrical output, and this is the series compensated line, series compensated characteristic. This is power here is given by P equal to V square by X into 1 minus K sine delta, and this is uncompensated line. Here power is given by that is represented this by this also, that is a V square by X sine delta, right? Now this is the power angle or transmission angle delta S1 at which my system is initially operating, and fault occurs. Then as soon as fault occurs, my system operates like this, delta S2. This is AS1 area, and then this is area. This is, for example, delta S3. This is area A2, which I will shade like this, AS2, not A2. And then this is delta S critical. And this whole thing, sole area is the margin of stability, AS margin. Let me explain now. I will explain the two systems simultaneously, side by side. I have two systems. Figure A represents the power angle characteristic of an uncompensated system, which is also represented by this dotted power angle curve. And figure B, this curve, represents the power angle characteristic of a series compensated system. Let us assume that the power transferred is 1.5 times P max. It could be even more than that. Let us assume that degree of series compensation is such that series compensated transmission line is capable of transferring maximum power of 1.5 times P max. Now take this uncompensated system and compensated system. Both the systems are operating initially at power angle or transmission angle of delta 1 or delta S1, when mechanical input provided by turbine is equal to electrical output. It's like this. This is the electrical output. This is my system, transmission system. This is sending in voltage, this is receiving in voltage. The mechanical input provided by turbine is equal to electrical output, and that is equal to electrical power transmitted over the transmission line or transferred over the transmission line. So electrical power which flows over the transmission line is equal to mechanical input. So there is absolute stability. The system is operating, whether it is an uncompensated transmission system or series compensated transmission system. The system is operating at steady state here, where PM is equal to PE. For uncompensated system, the transmission angle is delta 1, or for compensated system, it is delta S1. Let's assume a fault has occurred over this line. F stands for fault, and this line is tripped. Okay, it's out of the system. Line is tripped. When the line gets tripped, it does not transfer or transmit any power. So electrical power output becomes equal to 0, whereas the mechanical power input provided by turbine remains same. It does not change, it's constant. As a result of that, the rotor of the generator accelerates. The machine accelerates. Because of acceleration of the machine, the transmission angle increases. It goes on increasing in both the system, uncompensated system as well as series compensated system, like this. And for uncompensated system, when transmission angle is equal to delta 2, and for series compensated system, when transmission angle is equal to delta S2, the fault is cleared. And when the fault is cleared, the line is reconnected to the system. Okay, And during this process from delta 1 to delta 2 or delta S1 to delta 2, since the machine accelerates, it stores there is accelerating kinetic energy, okay, because of acceleration or due to the mechanical input which is there, but electrical output is zero. The machine accelerates and it stores the kinetic energy in its rotating parts, and that accelerating kinetic energy is given by area A1 for uncompensated system and area AS1 for compensated system. And as soon as transmission angle is equal to delta 2 for uncompensated system or delta S2 for series compensated system, we assume that fault is cleared. When the fault is cleared, the transmission line again gets connected to the system and it starts transferring the power. Now the question is, how much power will it transfer? Will it transfer PE equal to PM or higher? No, it will not transmit PE. It will transmit this much of, because it's not operating now at delta 1, it's operating at delta 2, or in this case delta S2. So it will transmit this much of power. In this case also it will transmit higher power. So now in this case, let us assume that power transmitted is PE dash, which is equal to PE, which is equal to steady state power. So PE dash is greater than PM. So the power transmitted or transferred over the line is greater than mechanical input. Electrical output is greater than mechanical input, and that will cause deceleration of the rotor of the machine. So machine will now start decelerating. And when machine decelerates, the transmission angle will still increase. It will increase from delta 2 to, for example, delta 3, and for uncompensated system, and for series compensated system, it will increase from delta S2 to delta S3 in such a way that decelerating kinetic energy, which is represented by area A2, it is exactly equal to accelerating kinetic energy represented by area A1 for uncompensated system, and for series compensated system, the decelerating kinetic energy represented by area AS2 is exactly equal to accelerating kinetic energy represented by area AS1. So for uncompensated system, when A2 is equal to A1, the system comes back to its steady state and it starts operating at this transmission angle and it transmits power PE, which is exactly equal to PM, and steady state operation again starts. It's restored, steady state operation is restored. And for series compensated system also, you can see when AS2 is exactly equal to area AS1, steady state operation is restored, and PE is exactly equal to PM, system comes back to its normal operation. Now, how much is the margin of stability for uncompensated system? It is a margin, and it is a small margin, which means that instead of clearing fault here, if the fault clearance was delayed substantially, it was not cleared here, it was cleared somewhere here, then the accelerating area or the decelerating area will never be equal to accelerating area, because because below this point you will have area, so for example, fault is cleared here, then this will be accelerating area, and decelerating area will be only this much, and decelerating area will be less than accelerating area, and when that happens, the system never comes back to steady state, and it becomes unstable. This is because of small margin of stability, a margin. Whereas in the series compensated system, you can see what is the margin of stability, AS margin. It is this much. It is very, very large as compared to the margin of stability for uncompensated transmission system. So that means even if this fault is not cleared here, it is cleared very, very late, you still have a very large margin of stability, and there is high probability that that system will still remain stable and it will come back to steady state operation. So therefore, these two figures clearly show us that when you compare these two figures, figure A with figure B, whereas figure A is power angle characteristic for uncompensated system, and figure B shows the power angle characteristics for series compensated system, it's very much clear that AS margin, that is the margin of stability provided by series compensated system, is much greater than A margin. It's much greater than margin of stability provided by uncompensated system, so that the system is more stable. The transient stability of the system is improved by series compensation. So this explains how series compensation improves the transient stability of the system, right? And the fourth advantage is power oscillation damping or electromechanical oscillation damping. Power oscillation damping. A series compensated system, just like a shunt compensated system, very quickly damps the electromechanical oscillations which are there because of some small disturbance. Okay, so this can be explained with the help of some figures. This is, for example, time axis, and this is transmission angle delta. Let us assume initially the system is operating at steady state at a transmission angle delta naught, which represents the steady state operation, and due to some disturbance the machine accelerates, decelerates, then again accelerates, decelerates. It's subjected to oscillations, because of which transmission angle also oscillates like this, in this manner. This is the oscillation of transmission angle around its steady state value delta naught. The question is, what is responsible for these oscillations in the transmission angle? That will be clear with the help of second figure, which I am going to draw now, which is P versus T. Let us assume the system, when the system is operating at its steady state at a transmission angle delta naught, it transmits or transfers the power P naught over the transmission line. Okay, a power P naught, which is the steady state power, is getting transmitted over the line. And let us suppose a small disturbance, a sudden disturbance or disturbances occurred over the system, which has reduced the power transmitted over the transmission line momentarily for some time, say for this much of time. Okay, because of this, because of P naught, because of, let's call this power as P dash, because of P dash momentarily becoming less than the steady state power P naught. That means P dash is less than mechanical input power. It has momentarily decreased from steady state value to this, which is less than mechanical input power. At steady state operation, power transmitted over the line is equal to mechanical input power. But when this disturbance occurs, the power transmitted is not P naught, it is P dash, which is less than P naught. Therefore, P dash is less than Pm. Electrical power transferred over the line momentarily decreases and it becomes less than mechanical input power. And since mechanical input power is more than the electrical output power, it results in acceleration of the machine. And when machine accelerates, the transmission angle increases. It reaches some higher value and then it should come back and settle, because when this disturbance settles, it should come back and it should transmit power P naught, and this should also come back and settle at delta naught, but that does not happen. If your system is uncompensated or undamped, then there will be permanent oscillations. The transmission angle will come back to delta naught, which is steady state value, and then it will become less than this, and then it will again increase, decrease, again increase, decrease. So the system is subjected to permanent oscillations, continuous oscillations like this, and you have to do something to damp these oscillations. So when system is subjected to oscillations in the transmission angle, there will be power there will be power oscillations also like this, something like this. So this results in a sort of instability of the system. Now the question is how to damp these power oscillations or electromechanical oscillations. For that purpose, you can use your series compensator. Series compensator will provide a degree of compensation K. How much degree of compensation it has to provide, that depends upon how much is the magnitude of oscillations and how much the power has dropped or reduced here below its steady state value. For example, from this point to this point, it will provide certain degree of series compensation. It may be 10%, 20%, we don't know. We have to actually calculate it, design it, and that much of compensation it will provide. And then from this positive peak to, this peak to this, there is no compensation. Compensation is zero. And then from this to this point, when delta is increasing, again compensation is provided. And when delta is decreasing during this period, no compensation. Then delta is again increasing. That means again series compensation is provided, and then delta is again decreasing, no compensation is provided, and then When the oscillations are over, that's it. Let me try to explain how the series compensation damps the electromechanical or power oscillations quickly. Initially, power has reduced due to some fault or some disturbance. Momentarily, it has reduced. That has resulted in acceleration of the machine, and delta increases. When delta increases, that means d delta by dt is greater than 0. The question is, when does delta increase? When mechanical input power is greater than electrical output power. Because that electrical output power is P dash, which is less than steady state value, and mechanical input power is excess. It is more than electrical output power. That causes acceleration of the machine. Delta increases, d delta by dt becomes greater than 0. And at this point, what will series compensation do? It will get connected. If it is a FACTS device or a series capacitive circuit, it will get connected in series with the line, and it will put certain capacitance in series with the line, and because of that, certain degree of series compensation will be there, which is given by xc by x. When a capacitive network is in series with the transmission line, the capacitive network has certain capacitive reactance xc, and xc by x determines the degree of series compensation. Let us assume this is the degree of series compensation, and when it provides the degree of series compensation, that means when the when the line is compensated, when XC gets connected, this was X transmission line reactance. Now when XC gets connected in series with X, this is JX, this is JXC, the overall reactance of the transmission line reduces. So the line impedance reduces, because now what is line impedance? Without compensation, line impedance is JX. With series compensation, it is JX minus JXC. So overall line impedance decreases, and therefore overall voltage between the two buses increases. When voltage increases and impedance decreases, the power transmitted over the line increases, because this P is given by V square by X into 1 minus K sine delta. Since this impedance has reduced, P, which is flowing over the transmission line, it will increase, and it will increase in such a way that it will balance the excess mechanical power. Because what was happening? Mechanical power was excess. It was more than electrical power transmitted over the line momentarily when this disturbance occurred, and that was causing acceleration of the machine, and that was causing delta to increase, making d delta by dt greater than 0. To reduce the delta, in order not to allow delta to increase, not to allow machine to accelerate, series compensation reduces the overall line impedance, and hence it increases the power transmitted over the same transmission line. And when electrical power over the transmission line increases, it balances the excess mechanical power. Okay, so the difference between PM and PE, it decreases, and that causes less acceleration of the machine. Machine is still accelerating, but not as much as this, and therefore delta is not increasing this much. This happens up to this. After this, you can see the delta decreases because the system is oscillatory in nature. When delta decreases, that means d delta by dt is less than 0. And when does delta decrease? Delta decreases when machine is decelerating. Now from this point to this point, machine was accelerating. From this point to this point, machine is now decelerating. And machine decelerates, delta decreases, so d delta by dt becomes less than 0. When does the machine decelerate? When electrical power transferred over the line is greater than mechanical input power. That causes, when electrical output is greater than mechanical input, that causes deceleration of the machine. And how can you make electrical output power nearly equal to mechanical input power? That means you have to reduce the electrical power transferred over the line, because it is greater than mechanical input power. How can you do that? You do that at this point by making series compensation equal to 0, by removing this series compensation. And when you are removing the series compensation, what is power transferred over the line? Power transferred over the line is, it's not V square by X into 1 minus K, because during this period, what is K? K is equal to 0. And when K is equal to 0, your equation was P is equal to V square by X into 1 minus K sine delta. When K is equal to 0, your equation now becomes P equal to V square by X sine delta. So overall line impedance now increases again. When this increases, the power decreases. And when power decreases, you may make it equal to mechanical input power, उससे machine की deceleration कम हो जाएगी. So machine will decelerate, but the magnitude of deceleration will be less. और फिर यहाँ से यहाँ you can again see that machine is again accelerating. When machine is again accelerating from this point to this point, your system will again connect the series compensator FACTS device in series with the line, and it will provide the series compensation with some degree K, and the magnitude of oscillation will be reduced with every passing cycle. It will be reduced, and finally all oscillations are gone. So therefore these are the sustained oscillations for undamped system. If there is no series compensation, this is undamped system, and these are the oscillations for damped system. How do you damp system? By providing series compensation, degree of series compensation like this. So same will happen with power. Power oscillations will also decrease. So this is undamped system oscillations, and this is damped. After 2 or 3 cycles, all the oscillations are damped, and P is again equal to P naught, delta is equal to delta naught, and system comes back to steady state. And at that time, you don't need any series compensation because all the oscillations are damped. This is how a series capacitive compensator or a series compensator, quickly within 2 or 3 cycles, very quickly damps the electromechanical oscillations which are there due to some disturbance in the system, and hence it stabilizes the system. Now as far as this series compensator is concerned, it operates in a bang-bang manner, because this degree of series compensation is adjusted between peak maximum value, minimum value, maximum value, minimum value, maximum, minimum. That is called bang-bang control. So this discussion very clearly explains how a series compensation helps in quick damping of electromechanical or power oscillations in a system. So these are the advantages of series compensation. In our previous lecture, we studied and we tried to understand how a shunt compensation technique is advantageous. Like, what are the advantages of shunt compensation technique? Like, shunt compensation technique results in increased power transfer capability, more voltage stability, improvement in transient stability, and power oscillation damping. The same advantages are offered by a series compensation scheme. Series compensation scheme, in today's lecture we have studied, we have understood that a series compensation scheme also offers the same advantages, that is increased power transfer capability, improved voltage stability by way of providing voltage support, improvement in transient stability, and power oscillation damping or electromechanical oscillation damping. Okay, so I advise all of you to go through this lecture and all other lectures. In case of any doubts, any queries, please feel free to ask. I wish all the best to all of you. Thank you.